All right, so our third double displacement reaction that you might encounter in the lab is the reaction of an ionic compound with an acid to form a gas. So this is like what we saw in our review question today, an ionic compound reacting with an acid to form a gas, usually carbon dioxide. So when you have a reaction with a metal carbonate, so anything carbonate, specifically you'll see usually calcium or, sorry, not calcium. Yeah, calcium or transition metals, probably not the sodium carbonate or any of the group 1A carbonates, but anything else, you'll probably see this kind of reaction. So we have um, a metal carbonate reacting with an acid to form carbon dioxide gas. So here in this example, we have copper carbonate reacting with HCl, and we're forming copper chloride and carbonic acid. And we've seen what happens when we form carbonic acid. Carbonic acid is not stable. It undergoes decomposition to form water and carbon dioxide. So our net reaction is the copper carbonate solid dissolving in hydrochloric acid to form copper chloride, water, and carbon dioxide. And that's what you see in this picture here. We have an acid, citric acid in this case, and base, which is sodium bicarb. So sodium bicarbonate is the same as your baking soda. So citric acid and baking soda reacting to form carbon dioxide gas, which you can see from the bubbles in the beaker. All right. So we can also write net ionic equations for gas-forming reactions. So again, our first step is to write a balanced chemical equation. And so that's the same as every other time we want to write a net ionic equation. So next, we identify the strong electrolytes, so strong acids and bases, or soluble ionic compounds, and write them in their completely ionized form. Then we identify our spectator ions and remove them to have what's left as our net ionic equation. So same steps as before. All right, so we have this reaction, which is hydriodic acid reacting with zinc carbonate to form zinc iodide and water and carbon dioxide, because we've seen our carbonate plus protons ends up with carbonic acid, which decomposes into our water and carbon dioxide. So when we write this in the fully ionized form, we want to find our strong electrolytes. So HI, hydriodic acid, is one of our strong acids, so it fully dissociates into hydrogen ions and iodide ions. Zinc carbonate is a solid, and carbonates are generally insoluble, and zinc is not one of the exceptions, so zinc carbonate is going to stay as a solid. Zinc iodide, on the other hand, iodide is generally soluble, and zinc is also not one of the exceptions. So that means that zinc iodide is soluble. So zinc iodide forms zinc 2 plus ion and 2 iodide ions. And then lastly, we still have our water and carbon dioxide, because they are not aqueous, they are liquid and gas, and we never take liquid and gas molecules apart. All right. So we find our spectator ions, which in this case are only the iodide ions. Everything else is needed on either side of the equation in something that does not dissociate. So we have 2 protons reacting with zinc carbonate. The protons came from our acid, and we're forming zinc ion, water, and carbon dioxide. That is our net ionic equation. The only thing we were able to get rid of was our iodide ion. Okay, When a gas-forming reaction involves an ionic compound that's not a metal carbonate, it's not as easy to predict the products. So generally, these will probably be given to you. But for example, a sodium sulfite solid reacting with, aqueous solution reacting with hydrochloric acid forms gaseous sulfur dioxide. So you can kind of see the parallel here. We had carbonate reacting to form carbon dioxide. Now we have sulfite, pretty much the same formula, SO3 instead of CO3, reacting to form sulfur dioxide. So there's a pattern here. And if we want to find our net ionic equation for this one, we're going to write out our completely ionized form, which I skipped here, but I did write our spectator ions in red. So sodium is one of our ions that's always soluble no matter what it's with. So it completely dissociates from sodium sulfite and from sodium chloride. And hydrochloric acid is a strong acid, so it completely dissociates. And that chloride ion is in sodium chloride on the product side, which also completely dissociates, like we said, for sodium containing compounds. So what we have left is the sulfite ion, the 2 protons from our hydrochloric acid molecules, our sulfur dioxide gas that we formed, and water. So just like with carbonate, with sulfite, we form sulfur dioxide and water instead of carbon dioxide and water. Okay, so not so bad, right? All right, so let's write our net ionic equation for the reaction between aqueous nitric oxide and solid barium carbonate. So nitric acid is HNO3, as we've seen several times, and it's aqueous. And we're reacting with barium carbonate. So barium is a 2 plus ion. Carbonate is a 2 minus ion. So they go together without any subscripts. And this is an acid reacting with a carbonate. So what are our products going to be? That's right, carbon dioxide and water, in addition to some salt. I'm sorry, that should be a solid. It says so right here. All right, so we're reacting. We're going to have a double displacement. So our nitrate ion is going to displace our carbonate ion. So we're going to end up with barium nitrate. So nitrate is a 1 minus, so that means we need 2 of them to balance out the plus 2 of barium. And for all carbonate acid reactions, we're going to form H2O and carbon dioxide gas. All right, so let's see what we've got. So nitric acid is a strong acid, so it fully dissociates. Oh, I'm sorry, we forgot to balance the equation. Very important step, can't forget that. Okay, so we have 2 nitrates on the right, so we need 2 nitrates on the left. So that gives us 2 nitrates on both sides, 1 barium on both sides, and carbon. So we have 2 hydrogens and a carbonate, which is going to, we take one of those oxygens away, add it to the water, add it to the 2 hydrogens to get water and leave carbon dioxide. Okay, so we only needed a 2 in front of our nitric acid to balance our reaction. So that means we need 2 protons and 2 nitrate ions. And then our barium carbonate is a solid. It's insoluble because most carbonates are, and barium is not an exception. And we're reacting to form barium nitrate. all nitrates are soluble, so barium nitrate is soluble. So I'm going to form barium ion, 2 nitrate ions, and water and carbon dioxide. Okay, so what can we get rid of? Do we have any spectator ions? So the only one I see is nitrate. So if we get rid of nitrate, our net ionic equation is going to be 2 protons plus barium carbonate reacting to form barium ion, water, and carbon dioxide. All right, so that's our balanced equation. This is going to be aqueous, this is solid, this is aqueous, this is liquid, and this is gas. We have all 4 states in this reaction. Pretty cool. All right, so that's it for chapter 9.3. So now we're going to talk about 9.4 in the next video.